Okay, so recap is that in the previous lecture, we started with first order, right? First order linear differential equations. And then we treated on the solution methods for this first order linear differential equations. So we spoke about integrating factors. Then we also spoke about Bernoulli equations. Okay. Basically, we spoke about two things. One, we have constant coefficients, and then two, when we have variable coefficients for first order differential linear equations, linear differential equations. So we spoke about these two types. When we have a variable coefficient and then when we have a constant coefficient. The next one is that we spoke about whether they are separable or not. We spoke about their separability. Then we spoke also about a minute. Then we spoke about initial value problem. So first, we started with something like y is equal to we started with something like, let me write it out clearly. We started with something like this: y prime of c is equal to a of c of y plus b of c. Then we said, okay, if a of c, b of c can be constant. Then the second one is a of c, b of c not constant or variable coefficient. Okay, they are variable coefficients. All right, this is what we spoke about. And we spoke about their solution methods. Okay, we spoke about their solution methods, how you can use the integrating factors, how you can also use. Then we spoke about initial value problems. So for initial value problems, resumes. Then we spoke about initial value problems. So initial value problem, we said we have y of t, a of t of y, okay? Of course, also of t plus b of t. And then we have some initial conditions. So we have yt0, which we can say is equal to y0. Then this becomes an initial value problems. Of course, in the same way, we can have constant coefficients and then variable coefficients also for the initial value problem. Okay, then we spoke about, after that, what we did was we spoke about the Bernoulli equation. Okay, so we spoke about Bernoulli. Bernoulli equation. And we said that the Bernoulli equation looked like this. That the Bernoulli equations look like this. So y prime of t, p of t of y plus q of t, y of n. Okay. And we said this is how the Bernoulli equation looks like. And then the idea behind Bernoulli's equation was simply for solving. So what the Bernoulli equation did was that if you have a nonlinear, okay, we know how to solve linear or linear differential equations. So if you have a nonlinear differential equations, you can actually transform, okay, transform this into a linear equation, transform to linear equation. And this is what, by applying Leibniz techniques. So, and this is what the Bernoulli's equation actually does. And this is why we learned the Bernoulli's equation where n is not equal to 1. All right. So after the Bernoulli's equation, then the other question we asked ourselves was on separability. We said, okay, we wanted to know if the equation is separable or not. So we studied separable equations. Okay, separable equations. For separable equations, we said h y of y prime is equal to g of t. Okay, separable equations where h and g are functions. So with that, we're also able to learn certain techniques for also solving separable equations. Okay. Then after that, what we did was we also tried to study the Euler homogeneous equations. Okay, so we said that sometimes the equation is not separable, but it can be transformed into a separable equation. Okay, so takes non-separable, okay, takes non-separable, and then makes them separable. This is what the we said, Euler homogeneous equation does. So if you have any differential equation, you can just try to make it separable. And then we said it was like n ty of y prime of t plus mty is equal to 0. You use such an idea to solve for your problem. And then also we treated how to solve Euler's equation in this form. So this is what we did for first lesson. We went through step by step all these methodologies and all these techniques up to where we are able to solve separable, non-separable equations. So today we are going to start with second order. Okay, second order. So today section 2. We'll start with second order linear equations. Okay, and a typical example usually for second order linear equation, a typical example is usually what they call the Newton's second law of motion, right? Newton's second law of motion, where we say that the force is equal to mass times acceleration. Okay, but why do we say this is a second order? Second order because your acceleration can be written in terms of the distance. So this will then become mass times the second derivative of the distance, the second derivative of time, okay? Which becomes the acceleration, which is the acceleration. So this is why we said this is the second order linear equation, because we have second, the highest order here being s. But in general, a definition for second order linear equation is given by y prime prime. Okay, let me not use the t here so that we have some uniformity. So y prime prime plus a1 of t of y prime plus a0 of t of y is equal to b of t. Okay. Okay, so this is your second order linear differential equation. So let me write it. So this is your second order linear differential equation. All right. This is the second order linear differential equation. So what do we say about this? We say that the coefficient A, okay, the coefficient, so some few things we can say that A1, A0, and B are given functions. On an interval I, which is real, oh, sorry, a minute, then we continue. On an interval I, which is in R, okay? Then we say that few things we say about this is so that one, we have that it is homogeneous. One, we say that it is homogeneous if B of T, okay, homogeneous if the source term B of T, if B of T is 0 for all T. Two, we say that constant coefficients, okay, constant coefficients if A1 and A0 are constant. Three, variable coefficients if either A1 or A0 is not a constant. Okay, so whenever any of the coefficients is not a constant, then we say that this is not a constant as well. Okay. Then next is that we take an example. If we take an example of a second order, then we can write something like 5y prime or 6 is equal to 0. So this example is we have 1. This example, we have a second order linear homogeneous. You can see it's homogeneous because this guy here is 0. 2 has constant coefficients because these and these are constants. And then a second example is that we have y prime prime minus 3y plus y, 3y prime plus y is equal to cos 3t. So we realize this is non-homogeneous. This is non-homogeneous. And then also we have we have constant coefficients, right? Constant coefficients. Okay. Then a third one is that if we have y prime prime plus 2ty prime minus ln c of y is equal to e3t, then we can say that this is non-homogeneous. Then we have variable coefficient as well. Okay. So in that case, if we go back to the force is equal to mass times acceleration, we can write mass as I wrote earlier on, the second derivative of time is equal to force, which then is dependent on time variable and then the first derivative. Okay, so another example is that we can say, example, find differential equation. Find the differential equation. Okay, that satisfies y of t is equal to c1 e4t plus c2 e minus 4t. Okay, where c1 and c2 are constants. So here, from the definition of y, we can compute c1. So c1 will be given by y e minus 4t minus c2 e minus 8. I take the first equation, the solution. I take the first equation and then I find the derivative, y prime. The y prime, if I find, will be equal to 4c1 e4t minus 4c2 e minus 4t. This is y prime. Okay. So we have y prime. Then what we do is that we can substitute C1 for the definition that we have written. So in that case, if we put C1 in, then we have y 4 times y e minus 4t minus C2 e minus 8t all times E4t minus 4C2 E minus 4t. So immediately you see that they cancel out. So we have 4y, and here as well, we have 4C2E minus 4t. All together 4C2E minus 4t. So you can factorize, you can just check it out. You can see that these two here are the same. So you can write this as 4y minus 8 C2E minus 40. And that gives us a value for C2. So C2 will now be 1 over 8 of 4y minus y prime. Okay. So now we have C1 and then we have C2. Now we have C1, we have C2. So so now we have C1. C1 is here, and then we have C2. C2 is here. Okay. So now that we have C1 and C2, we can go back and then no. So actually now, although we do not need it, so at this point we have computed C1 in terms of C1 we computed in terms of Y, okay, and Y only Y. So now our next ambition is to compute C1 in terms of Y prime and Y, okay, Y prime and Y. So what do we do? So we know C1 is given by this. So now we know C1 will be YE minus 4t or minus C2, which is 1/8 of 4y minus y prime, all times e to the power minus 8. Okay. No, so it's sorry, here I missed the step. So this is e minus 4t, and then this is e minus 4t. I hope it's correct. Let me check. So this is that. This that. This is that. This is that. 4. Yeah, I think so. This is correct. So C2. Oh no. So this here should be plus. All right. Now this is correct. So now this is plus, and then this is plus. So this is correct now. And so we can really go ahead and write YE minus 4t minus 1 over 8 into bracket 4y minus y prime exponent minus 4t. Okay. minus 40. So now if we have this, it means that we have C1 now in terms of y prime inside there. So we can go ahead, we can go ahead and then compute the derivative of that one. So what we do is that now we say we have the derivative, we want to compute the derivative of C2, and this will be half 4y minus y prime of e to the power 40 plus 1/8 4y prime minus y prime prime e to the power 40. And this is equal to 4 into brackets 4y minus y prime plus 4y prime minus y prime prime is equal to 0. And this will yield finally y prime prime minus 16 of y to be equal to 0. So this is 16. Which is then the solution of the problem that we are seeking. So this is y prime prime, y prime prime 16y is equal to 0. Okay. I hope this is clear. So is that? Okay. So I go over briefly again. Briefly, I'll go over again. Okay. We want to find the differential equations that satisfy this solution. First step, take C1. Make C1 the subject of your equation here. This equation, let's call it A. Okay, let's call this A. Make C1 the subject. When you do that, you have C1 is equal to this. Then, second step, find the derivative of A. Okay, find y prime from A. Okay, this is A. Find the y prime. If you find the y prime and you do your simplification, you should get y prime of t is equal to this guy here. Okay, you should get this here. Then when you have this, now make C2 the subject, okay, of this equation. Okay, so make C2 the subject of this equation. If you do that, you get this, which we call equation 2. So you have C1, you have C2. But C2 now is in terms of y and y prime. So the question is that we want to make C1 also in terms of y and y prime or something similar. So we now substitute C2 into our equation C1. If we do that, we get this guy here, okay? Then we find the derivative because it's a constant. Okay, we find the derivative. C2 is a constant. We find the derivative, which gives us finally this equation, which is actually the solution or the equation for the solutions that we already have. Second equation, we take y. Second equation, we write y of t is equal to c1 over t plus c2 times t. So the same way, first find the derivative. Okay, find y prime. If you find y prime, you get this, and then you can make c2 the subject. All right, already. Then now substitute your c2 into your main equation. If you do that, you'll be able to arrive at this guy here. So you have y of t, okay, y of t you have this, okay, you have this, and then make c1 the subject. So if you make c1 the subject here, then what you have half of ty and minus t squared y prime. Then the next step is that find the derivative of this c1 now that you have. Okay, so find the derivative. If you find the derivative is a constant, so it's equal to 0. It is 0. If you find the derivative of a constant with respect to time, it is 0. Now, if you go here, you apply your differential rules. And then once you apply them, you come to the final solution, which is what we are looking for. Okay. Is someone saying there's no sound? All right. So the next step is that we want to solve for initial value problems. Okay. Initial value problems. Here we say that for second order linear differential equations, you have solutions in the case that the equation coefficients are continuous functions. And since the solution is already unique, when we specify two initial conditions, the general solution must have two arbitrary integration constants. This is what we mean. So the theorem is that if the functions a1, a0, and b are continuous on a closed interval I, which is in R, the constants C0 in I and Y0, Y1 in R are arbitrary constants. Then there is a unique solution Y defined on I of the initial value problem y prime prime plus a1 of t y prime plus a0 of t y is equal to b of t, and then we have y of t0 is y0, y prime of t0 is y1. Okay. So for second order linear differential equations, we usually have two initial conditions. Okay. So example, if we have t minus 1 y prime prime, t minus 1 y prime prime minus 3 cy prime plus 4 c minus 1 over c minus 3 all y is equal to t into bracket t minus 1. Then we have y2 is equal to 1. Y prime of 2 is equal to 0. Okay, so if you have such a problem, then we first write the equation in the form of how we saw the theorem. Okay, okay. So what do? You write y prime minus, so this is the solution, minus 3t over t minus 1 y prime plus 4 over t minus 3 y is equal to t. Okay, so question is, what is the interval or the domain for the interval for the coefficient? Okay, so we see that the coefficient, the first one, is between minus infinity and 1. Okay, then we see that we have another coefficient which is 3. So it means we are from 3 to infinity. And then we have from between 1 and 3 as well. So this is actually the domain of the coefficients. Okay, that means that the solution is not defined. Okay, so undefined solution at t is equal to 1 or t is equal to 3. Okay, so now the next step is that okay, so now we have initial condition T0. Okay, so initial condition T0, 3. You have initial condition T0 is equal to 2. It belongs to, it's part of the domain. Okay, it's part of our domain. So you see that so you see that the initial condition is 2, which is part of our domain. And then we have rewritten equation in terms of how the second order linear equation looks like and found the domain here. So those are the critical things that we need to look out for. Okay. Now the next step is that we want to talk about properties. Properties of homogeneous equations. Okay, so but before we get into the properties, before we get into homogeneous equations, let's first write this down. So we have Ly is equal to y prime prime plus a1 of ty prime plus a0 of ty. And let's call this let's call this 1. Okay, so example is that we can have Ly is equal to Ty prime prime plus 2y prime minus 8 over Ty, okay? And then acting on y of t is equal to tq. Solution is that we know y of t is equal to tq. So y prime of t will be equal to 3t squared, and y prime of t will be equal to 6 of t. So L of tq, okay, will now be equal to t. We said we have y prime, which is 6t, and then we have 2y prime, which is 3t squared, minus 8 over 8 of y, which is this cube. And this will be 6t squared plus 6t cubed minus 8t squared. And all of that, I hope I'm correct. Sorry, this is t squared. So this is 6t squared ty prime plus 2y prime so all of that will be 6 plus 6. So this will be 4t squared. Okay, 4t squared. So theorem for linear operator. So if you have the operator, if you have an operator L of y to be y prime plus a1y prime plus a0y, where a0, a1 are continuous and y is twice differentiable, is a linear operator. Okay, so the proof for linear operator is very, very straightforward. You should be able to check one, C1, Y1, C2, Y2. Okay, if you do this, you should be able to get C1, L, Y1 plus C2, L, Y2. Okay, so very, very easy to check. Very, very easy to check. Then we have another theorem. So this is the theorem of the linear operator. That if you have an operator L of y, which is given by the second order linear differential equation, where the coefficients a0 and a1 are constant and y is twice differentiable, then this satisfies a linear operator. Okay, and then you can prove it. And the second one that you should know, is called superposition. Okay, superposition. So for superposition, what it says is that if L is a linear operator, and y1, y2 are solutions of the homogeneous equation Ly1 is equal to 0, Ly2 is equal to 0. Then for every constant C1, C2 holds, okay? So for superposition, it holds that C1, Y1, C2, Y2 is equal to 0. Okay. Okay, so in this case, I mean, the proof also follows similar to this guy. All right, if you have your L, you just make your substitution. So you see, if you want to prove this guy, you write L C1 Y1 plus C2 Y2. Then wherever there is Y and that, you just make the substitution. That's the only thing you do. Okay, so that's the most important thing you just substitute. You do C1 Y prime prime of 1 plus C1 A1 C1 Y prime plus A naught C1 Y1 plus then the same thing for C2. So the same way, this proof also follows in a similar manner. Okay. Of course, I forgot to write the main property. The main property that if we define definition that if we have an operator, okay, if you have an operator L, then we say that it is linear if and only if every pair of functions y1, y2, and constants c1, c2, it holds that we have L c1, y1 plus c2, y2 should be equal to c1 L y1 plus c2 L y2. So this is a definition that I forgot to say, because that's all that we are using here for the operation, for the operator, for the proof. And then also for this one, we use the same definition, okay? So we now introduce the notion of, so next, we introduce the linear dependent and linear independent functions, okay? So next, we introduce linear dependence, linear dependency, okay, of solutions. Okay, linear dependence of solutions. The definition, if we have two functions, y1, y2, we say they are linearly dependent. Dependent if and only if they are proportional. Proportional. proportional, okay? Otherwise, they are linearly independent. So remarks. Two functions y1, y2 are proportional if and only if there is a constant C such that for all T holds y1 of T is equal to C y2 of T. B, the function y1 is 0, is proportional, okay, to every other function. Y2. Since y1 is equal to 0 is equal to y2 holds. So linear independence, linear dependence okay. So we said two functions y1, y2 linearly independent if and only if they are proportional, otherwise they are not. And then sometimes also two functions are said to be linearly, two functions are said to be linearly dependent on an interval I if and only if there exists constants C1, C2, which are both non-zero, okay? Such that C1, Y1 of T, C2, Y2 of T is equal to 0. So example, show that Y1 of T is equal to sine T, Y2 of T is equal to 2 sine T, are linearly dependent. solution y1 of t is equal to sine t. y2 of t is equal to 2 sine t. But we know sine t is equal to y1. So this is basically 2y1. In that case, we can write 2y1 of t minus y2 of t is equal to 0. Okay. So very, very basic example, simple example. Okay, then what about an example for non-linear independence? Okay, linearly independent. So if we take y1, of t to be sine t, and we take y2 of t to be t sine t. Okay. And can we show that this is linearly independent? So solution, we need to find some constants C1, C2, C in all R holds C1, okay, Y1 plus C2, Y2 is equal to 0. All right, this is what we need to prove. We need to show that. So if I take C1 and I take sine T, then I take C2 and I take C sine T, I should get 0. Okay. So if we take C to be pi over 2 and T to be 3/2 of pi, then we will have C1 plus pi over 2 of C2 is 0, and we will have C1 plus 3/2 of pi, C2 is 0. If we have such an equation, then it implies that C1 is 0, C2 is 0. And thus, we say thus Y1 and Y2 are linearly independent. Next, we say that if you know two linearly independent solutions to a second order linear homogeneous differential equation, then you actually know all possible solutions to that equation. And any other solution is just a linear combination of the previous two solutions. Okay, and then we repeat that the equation must be homogeneous. Don't forget, I just said that. And this is really closer to the general solution, second order linear solution. Okay. So next, is that we are going to check how do we test for linearity of two solutions. Okay, test for linearity of two solutions for second order differential equations. And then we'll compute the Wronskian of two given independent solutions, and then compute the first order differential equations from second order using Abel's theorem. Then we use the order reduction method also for the second order differential equations with initial conditions. So this is what we are going to discuss next. All right. So 2, I don't know whether it's 2.2 or 2.3, but the general solution says the general solution that if you have y1 and y2 such that they are linearly independent solutions, of L of y to be equal to 0 on an interval I in R, where L of y is equal to y prime prime plus a1 y prime plus a naught y, where a1, a naught are continuous functions on I. Then there exists unique constants, okay, C1, C2, such that every solution y of the differential equation L of y is equal to 0 on the interval I can be written in a linear form, okay, as a linear combination y of t is equal to c1 y1 of t plus c2 y2 of t. But even to prove that, we create a definition to state the following, that the function, okay, the functions y1 and y2 are what we call fundamental solutions of the equation L of y is equal to 0 if and only if y1, y2 are linearly independent and Ly1 is 0 and Ly2 is also 0. Okay, so this is the general solution definition part A. I go to B. So we say that the general solution of the homogeneous equation L of y is equal to 0 is a two-parameter of functions ygen given by yg. So let me just make it a general solution, okay? So I say y of g, the general solution of t is given by cy1 of t, c2y2 of t. Okay, where c1, c2 are parameters of family, and y1, y2 are fundamental solutions of Ly is equal to 0. Okay, example is that show that y1 et and y2 e minus 2t are fundamental solutions of y prime prime plus y prime minus 2y is equal to 0. Solution. We first show that that y and y1, y2 are solutions to the differential equation. So first, show that y1, y2 are solutions. So take L, y1, go to y1 prime prime, y1 prime, 2y1 is equal to et minus et minus 2et, which is equal to 0. L1. Now L2. L2, y prime prime 2 plus y prime minus 2y2. And this is 4e minus 2t minus 2e to the power minus 2t minus 2e to the power minus 2t, and this is 0. Next, we do 2.1.4 is the Wronskian. Wronskian function. Okay. So the Wronskian function, let's denote by W the Wronskian function. Okay. So definition, the Wronskian of the differentiable functions y1, y2 is given by W y12 of t is y1 of t, y2 prime of t minus y prime, 1y prime, and then y2 of t. So remark is that we have a matrix AT which is given by y1 of t, y2 of t, y1 prime of t, y2 prime of t. Then the Wronskian is nothing but the determinant. So W12 of t is nothing but the determinant of A of t. Which is sometimes written as y1, y2, y1 prime, y2 prime. Example, find the Wronskian where we have of y1 of t, which is equal to sine of t, and y2 of t is equal to 2 sine of t. Solution 1 y2 of t is y1, y2, y1 prime, y2 prime. This is nothing but sine of t, 2 sine of t, and here we have cos of t, and here we have 2 cos of t. To find the determinant, then we have sine of t, 2 cos of t, minus cos of t, 2 sine of t. Then we say that W12 you see is equal to 0. W12 of t is equal to 0. So y1 and y2 are linearly dependent. Okay. But in the case where y12 of t is not equal to 0, we observe something. We observe linear independence. Okay, we write again what we call the Wronskian one. That if we have linearly dependence, then the Wronskian is 0. Okay. If y1, y2 are linearly dependent on the interval I and R, then the Wronskian is 0 on the interval I. Note that the converse to this theorem, okay, which is Wronskian 1 theorem, false. Thus, if W1, 2 is 0 for all T on I, does not imply that Y1 and Y2 are linearly dependent. A typical example is that if we have Y1 of T to be T squared, and have Y2 of T to be this for all T in R, then you can show that they are linearly independent and have Wronskian is equal to 0. Okay. Then you state a small corollary for Wronskian 1 that says that if the Wronskian with respect to an initial time step is not 0 at the point T0 in I, then the functions Y1, Y2 defined on I are linearly independent. An important property that we want to show with regards to computing the Wronskian is what we call the Abel's theorem. Okay, so this is a theorem where we say if Y1, Y2 are twice continuously differentiable, solutions of Y prime prime plus A1T of Y prime plus A0T of Y is equal to 0. Was where A1 and A0 are continuous on I, this is R, then the Wronskian W1 to satisfies W prime 1, 2 plus A1 of T W1 2 is equal to 0. So therefore, for any T0 in the interval, the Wronskian W1 2 is given by the expression W1 2 of T W1 2 of T0 E minus A1 of T. Okay, where A1 of T is nothing but integral T0 to T A1 of X ds. Okay, the proof is very straightforward. So proof is very straightforward. If you compute the Wronskian, so 1, compute the derivative of Wronskian. This is if you compute W1 2 prime, it will be Y1, Y2 prime, minus Y1 prime, Y2 up prime, Y1, Y2 prime prime, minus Y1 prime prime Y2. All right. Then we recall, so we stop very soon. We recall, okay, so recall that both Y1 and Y2 are solutions. So we have Y prime prime is equal to minus A1 Y prime 1 minus A naught Y1, and then this is Y1, then we have Y2 prime prime is minus A1 Y2 prime minus A naught Y2. Next, replace. Then you go back to your Wronskian, you make your replacement Y1 minus A1 Y2 prime minus A naught Y2 minus A1 Y1 prime minus A naught Y1 or Y2. And this is equal to minus A1 Y1 Y2 prime Y1 prime Y2. And then so we obtain W prime 1, 2 plus A1 of T W1, 2 is equal to 0. This equation and this is first order linear equation. That can be solved using, for instance, integrating factors. Okay, can solve this using integrating factors. So, example, t squared y prime prime minus t plus 2 y prime plus t plus 3 of y is equal to 0, t is equal to 0. So first, write it solution. Write it in terms of t plus 2 over t squared of prime plus t plus 2 over t of y is equal to 0. Then you have y prime prime. Now you can write this as 2 over t plus 1 y prime plus 2 over t squared plus 1 over t y is equal to 0. I hope I'm correct. T.
I don't think so.
So this is t, then you have 1 plus 2 over t. Is that you don't think so?
The one attached with y.
Ah, okay, the one attached to y. And we have, okay, yes, you're correct then. That one we have 2 over t plus 1, right? Also. Sorry, it should be squared. It's squared. It's squared. Or?
Yes. Yeah, I think so.
So it's t squared, 2 over t squared, and 1 over t. So it's correct. I made a mistake. Right? Yes, then that's correct. Okay. Then if we use a theorem, then using the Wronskian, we write W12 prime of t minus 2 over t plus 1. W12 of t is equal to 0. So this is a okay. So now we write it in the Wronskian form again, and then if we write it, we get this equation, which you can now apply your knowledge from integrating factors. Okay, so now solve using integrating factor method. You can solve this. It's very straightforward. Okay, so finally, we'll stop here, and then Friday we'll continue. All right, we'll stop here, and then Friday we'll continue from here. This example here, because now all we need to do is to find the integral of this term here, ds, and this is minus 2 ln t over t naught minus t naught, which is equal to ln t over t naught minus t naught, sorry, squared, okay, t minus t naught. And then we can now use, okay, the integrating factor method. So we take an integrating factor of t naught squared over t squared e to the power minus t naught. And then this satisfies mu of t naught is equal to 1. Okay. So the solution W12 is given by mu of t W12 of t prime is equal to 0. And this is mu of t W12 of t minus mu of t naught W12 of t naught is equal to 0. Okay. So the solution will be W12 of t is equal to W12 of t0, which is t0, t squared of t0 to also squared e to the power t minus t0. And then if we choose a constant, if we let the constant c to be equal to W12 t0 all over t0 squared e to the power t0, then the Wronskian has a simpler form y12 of t is equal to ct squared e to the power t. Okay, so with that, we're able to write the solution for this problem.